In Lab 7, you're going to get to create your first sequential circuits. So circuits that make use of memory elements. In particular, in experiment 13, you'll be using D flip-flops, as in data flip-flops, and in experiment 14, you'll be using T flip-flops, as in toggle flip-flops. And recall from the textbook and from the lectures, you can look at how to create a D flip-flop or a T flip-flop in VHDL directly in the textbook. Okay, so this first experiment, experiment 13, is a simple data latching and display circuit. And you could see the top level black box diagram right here. So as with all of our circuits, you'll start by drawing out boxes for your inner structural modeling diagram of how you're going to create this design. So the whole goal that you want to have happen for this design is using the 8 switches as an RC number. You want that RC number displayed on the 7-segment display. So you'll get to make use of your 7-segment display module again. Now you're probably saying, yeah, I know how to do that now. I did Lab 6, and I know how to get an RC number displayed on the 7-segment display. So that's all fine and dandy. But now what we're adding in here is the notion of remembering the number that you had. So in this case, let's say you have all your switches set to 0. What does the display show? It shows the number 0. Now let's say you make all your switches all zeros and then a 1. So in your old experiment, the display would show a 1 as soon as you flipped that switch. But in this experiment, we are not going to show that new value until you push the button. So the effect of pushing the button is saying, okay, I want the circuit now to latch in the value that's on the switches into my circuit or into my flip-flop, so that way my new value is now remembered. Now I have the 1 displayed on the 7-segment display. Now I could flip the switches as much as I want, and they're not going to change the display because the display is remembering, or rather my circuit is remembering what value I had. And then when I push the button is the only time my new value from the switches will get displayed on the 7-segment display. So that's what your goal is for this first experiment. And you can make use, create a D flip-flop, and then make use of as many D flip-flops as you need in your design, in your structural model. Okay, experiment 14 is creating a 4-bit counter based on T flip-flops. And the idea here is to use a T flip-flop and figure out what is the T logic, or the logic for the input to the T variable of the T flip-flop, in order to create a 4-bit counter. So you basically want this counter to count from 0 to 15 and roll back around to 0 again when it is enabled. So in this lab, you're going to create a T flip-flop module, which will look very similar to the T flip-flop in your textbook, with an enable signal. And you'll instantiate 4 of those in a structural model diagram to make the counter. So since it's a 4-bit counter, we need 4 T flip-flops to hold each of the 4 bits. And so the whole idea of using the toggle flip-flop is, here if you look at the binary of 0 through 16 or 0 through 15 using 4 bits, you can see the least significant bit is toggled at every transition, from 0 to 1, from 1 to 0, etc. The next least significant bit is only toggled every other time. So it's toggled between the 1 and 2, between the 3 and the 4, between the 5 and the 6, etc. And then you could see that for the next bit, it's only toggled every 4 times. And the way I see it is, you can look at it that this bit, or your second least significant bit, is only toggled when the least significant bit is a 1. And the next bit here is only toggled when these 2 are 1s. So you can see here it goes from 0 to 1 when these 2 are 1s. It goes from 1 to 0 when these 2 are 1s. And then also for the most significant bit, it's only toggled when the bottom 3 are 1s. So keep this in mind. This might give you a little hint of maybe how to go about implementing this circuit. Okay, so what you're doing with this circuit is you're creating the 4-bit up-down counter. The enable signal is used to say, okay, when your enable is high, so this is going to be mapped to a switch, then your counter is just going to automatically count. So every clock edge, hence why there's a clock, it's going to jump up from 0 to 1 to 2 to 3, so long as the enable is high. Then if you turn off the enable, or put down the switch, then the display will just show whatever number it was, and it will just sort of freeze or hold that state. And then you turn it on again and it starts counting again, and turn it off again and it holds the state. So that's the whole goal, and you'll see here that you're also going to be adding a clock divider circuit to take the clock from your board and divide it down to a slower speed, so that way you as a human can actually see this clock or this count happening, because you don't want it to be counting at 50 megahertz because you're never going to see all those changes. So we probably want to make the clock go down to like a half second or something so you can actually see it going from 0 to 15 and back around to 0. Alright, so those are the two experiments for this week's lab. I did want to go over in iSim how to use a clock, because remember in iSim we've always been getting rid of these clock processes when doing our test benches. But now that we're doing sequential circuits, we need those. Okay, so here I have in iSim, what I've done here is I've created a D flip-flop module that has a D and a clock input and a Q output. And there's my architecture. You've seen this in the lecture and in the textbook. If rising edge of clock, then Q gets D. So let's say we did want to add like a button enabler to this flip-flop. I could do it here. Be sure to add it to my sensitivity list. And so if I only wanted Q to get D when the button was pressed, I could do something like this, having a nested if statement. If button equals 1, then if rising edge of clock, and if, and if. So this is, I'm just showing you how you could add an additional enabler to your flip-flop. Okay, so let me go ahead and synthesize this. And that came out good, so let me now create a test bench module. We'll call it my test bench for my flip-flop. Okay, here's my test bench. So remember before we've been deleting this clock period? Well, in this case we're going to leave it here. So this clock period is saying it's 10 nanoseconds, which is for simulation purposes. So every 10 nanoseconds you'll see another low to high transition on the clock, which I'll show you when I create the waveform. Then we have this clock process definition, which we're also going to keep. This is what's creating that low to high clock pulse. So you can see it's low for half of the clock period and then high for half of the clock period, which creates this consistent up-down signal which acts as my clock. And we'll see that also in the waveform when I run it. Okay, so now we can enter our stimulus. Remember we have a clock, button, and D, so I'm just going to put in some dummy things for just showing you or illustrating this purposes of this clock and the D flip-flop. So let's go ahead and first enable our button and make D a 1. Then we can wait for a while. So if we wait for 30 nanoseconds, 3 clock periods will go by, and then we could say D gets 0, and then wait for another, I don't know, 20 nanoseconds. I'll keep it at 30 so we can be consistent here. Then we'll make button get 0 and D get 1. And then we'll make button get 1. Okay, so what should happen here? Nothing's going to happen for the first 100 nanoseconds, and then we're going to enable the button and make D 1, which means that our output Q should get 1 because both button and D are 1. Then 30 nanoseconds later, D will get 0, so Q should get 0. 30 nanoseconds later, we're turning the button off. So even though D gets 1, Q will not get 1 because button is not enabled. But then we go ahead and enable it, and since D is 1 at that point, Q should become 1. So let's see if this happens. So if we go to the simulation tab, I'm going to go to my test bench. I have a couple here because I was playing around. Simulate the behavioral model. Yes, please. And let's go ahead and click on the zoom full and go to the beginning. So you can see here, here's this clock pulse. And because we set our period to 10 nanoseconds, you can see here, this is 10 nanoseconds. That is one clock period, a low and a high together. So you see the clock has a very regular low to high every 10 nanoseconds. And that time frame is set by that clock period variable that we saw in the test bench VHDL file. Okay, and then we said for the first 100 nanoseconds, so let me show you that again. We waited for 100 nanoseconds first, so that's why our output Q, we have no idea what it should be because we did not enable the button yet. The button's 0 and our D is 0. Okay, so now at 100 nanoseconds, we've enabled our button and we've also made D a 1. Now you can see though that Q doesn't become 1 until the rising edge of the clock, which happens at 105 nanoseconds, which makes sense because in our D flip-flop definition we have a rising edge of the clock. So here we are, our button got 1 and D got 1. Now 30 nanoseconds later, D is going to become 0. So 30 nanoseconds later, which would happen at 130 nanoseconds, D becomes 0. And look, Q becomes 0 at the rising edge of the clock, so that makes sense. Then 30 nanoseconds later, we set button to 0. So because we set button to 0, even though D became high, Q did not become high. You can see Q is still 0 because the button is 0. But then 30 nanoseconds later, I set button to high again, which means then at the rising edge of the clock, Q can get whatever D is. So this shows us that our flip-flop was working as intended. So the point of this was really to show you about how to use these clock processes for sequential circuits in your iSim waveform. So what I'm looking for in the lab write-up is that you'll write up everything for experiments 13 and 14. I only need to see an iSim waveform for experiment 14 and a live video demo for experiment 13. Have fun!